Ask a large language model for a Python script, and you might get perfect executable code. Ask the exact same question tomorrow, and you might get a 5-paragraph essay explaining Python. Relying on ad hoc natural language queries creates fragile, non-reproducible outcomes in a software engineering workflow. The primary failure mode happens when we treat the LLM as a conversational agent. Software engineering requires precise, programmatic execution, but LLMs are built to chat. A 2023 paper by White and colleagues addresses this exact friction. They demonstrate that integrating large language models into software pipelines requires applying strict, formal constraints to the inputs. To solve this, the researchers define the prompt as a composite, programmable function, resulting in this transformation equation. Output equals the LLM processing S plus R plus omega plus I. Each of those variables inside the parentheses represents a specific modular constraint layer applied to your baseline query. This mathematical structure redefines the prompt as a series of instructions passed through a pipeline rather than a conversational thread. Treating prompts as formalized software pipelines allows engineers to extract predictable outputs from a probabilistic model. Visualizing this formula, variables S for scoping and R for role expand into bounding boxes, constraining the LLM to a specific domain. The variable I, your input, is placed inside. Finally, omega, the output automator, acts as an exit filter for automated pipelines. LLMs naturally want to converse. They prepend code with phrases like, "Sure, here is your code," and append it with explanations. That conversational bloat immediately breaks downstream parsers and CI/CD pipelines. An output automator acts as a strict structural filter, forcing the LLM to strip away conversational prose and return only the requested format. You apply this by explicitly demanding an executable bash script, pure JSON, or a requirements.txt file. Output automators are the exact mechanism that converts an unpredictable chatbot into a tool capable of integrating headless into automated software pipelines. Applying this framework to code quality exposes another challenge. Left to their own devices, LLMs generate functional but unstructured monolithic outputs. We can correct this using the principled code pattern, which is a specialized application of the scoping variable. Explicitly appending design constraints, specifically demanding adherence to solid principles, forces architectural rigor onto the output. Consider applying this pattern to legacy code. Enforcing the principled code pattern forces the LLM to execute interface segregation and dependency inversion. The central monolith visually fractures into smaller, distinct modules with clean interfaces and injected dependencies. Without explicit principled scoping, LLMs optimize purely for functional completion over maintainability. Enforcing these constraints is mandatory to generate enterprise-grade architecture. Asking an LLM to directly translate complex, technology-specific logic carries a high cognitive load and drastically increases the risk of hallucination. The intermediate abstraction pattern bridges this cognitive gap. This pattern maps directly to the mechanical logic of the Gang of Four adapter or bridge design patterns, which decouple an abstraction from its implementation. First, we instruct the LLM to map the technology-specific problem into a language-agnostic mathematical model, abstracting dense code into a general state machine diagram. Then, the second phase restricts the model to generating target language code strictly from that abstracted logic. A complementary tool in this domain is the hidden assumptions pattern. This acts as an audit tool that surfaces implicit execution constraints, such as assumed memory limits or file size caps. Explicitly managing the abstraction layer prevents the model from making silent, catastrophic assumptions about the execution environment before the code reaches production. When it comes to bulk refactoring, instructing an LLM to rewrite a massive function in one shot almost always results in lost control flow and degraded logic. To mitigate this risk in legacy codebases, we use a multi-step strategy called pseudocode refactoring. This pattern mirrors abstract syntax tree lowering in compilers. Step 1, abstract source code upward into high-level pseudocode, capturing computational intent. Step 2 requires human-in-the-loop verification of this logic. Finally, Step 3 lowers the verified pseudocode into the refactored target language. Separating logic extraction from syntax generation allows engineers to safely execute large-scale LLM refactoring without destroying the original control flow. This formal equation powers 13 distinct prompt patterns. As we can see in this 4-quadrant matrix, they span the entire software development lifecycle, from code quality and refactoring to system design and requirements elicitation. In the early elicitation phases, patterns like the requirement simulator and specification disambiguation force the LLM to surface ambiguous terms and test edge cases before a single line of code is written. However, this framework operates under strict technical limitations. Finite context windows remain the primary bottleneck. A restricted prompt window requires large legacy files to be chunked into smaller segments before ingestion. Additionally, temperature settings and continuous model updates create inherent non-determinism in the outputs. Because of this non-determinism, LLMs function strictly as assistants. Every pattern in this framework demands rigorous human testing and validation. Utilizing output automators, enforcing architectural principles, and mapping workflows to CS fundamentals allows engineers to program these models with formal rigor.